First, we are going to go to geogebra.org. Geogebra.org. And then on the bottom corner here in the middle, you're going to click on geometry. First, click on the circle with center. Here's a center. Drag out and make a circle. Then I'm going to construct a line going through the point A and B. And make sure it snaps to the point, and you will know. I'll tell you how to check to make sure you did it correctly. So click on move, and when you move the point B, the circle and the line should move together. Then I am going to put a point where the circle and line AB meets. And again, you know that you did it correctly. When you move point B, point C also should move. Then I am going to put a point somewhere on the circle. And then connect point C and D with a segment. C and D. And I'm going to connect points B and D with another segment. So you did it correctly if you can move point D and both segments move at the same time. If you move point B, circle, point C, and everything moves together. If they are not together, then you have done something wrong and you need to fix it. Then I want you to click more, and at the bottom it says measure, and I want you to measure the angle CDB, and that angle is over here. And in order for us to measure the correct angles, you can't just click D there. You have to tell GeoGebra precisely which angle you want to measure. So you have to go from C, D, and B. And notice it says that it is a 90-degree angle instead of a little arc there. There's a little square box showing that it is 90 degrees. Then you know that you did it correctly. If you move point D, the angle stays at 90 degrees. Okay, we have constructed the diagram that you see on the left side here in GeoGebra, and we have seen that angle ABC in this case is 90 degrees. No matter what, I can move this point B anywhere along the circle, even down here, it'll always stay at 90 degrees. So the triangle inscribed in a circle when one side is a diameter is always going to be a right triangle. We are going to prove that statement, start from a given information or something we know, and logically follow step by step and lead to a conclusion. And in our case, we're going to start with something obvious from the drawing and then lead to this last statement, the measure of angle ABC is 90 degrees. So let's start. So what I notice here is that AC is the diameter. That means OC and OA are radii of a circle, and they are congruent. So I'm going to mark, perhaps using a different color here, mark OC and OA as congruent. But I have another radius that I see. It's going to be OB. So I'm going to draw OB and mark that as a radius as well. So the statement that I can use is going to be OA is congruent to OB, which is congruent to OC, because they are all radii of the same circle. Okay, radiuses or radii, they're the same thing. And so because I know that OB and OC, for example, are congruent, that makes this triangle that I'm highlighting right now, triangle OBC, an isosceles triangle. Triangle OBC is isosceles. And the reason I know that is because OB and OC are congruent, and that's the definition of an isosceles triangle. Okay, because it's an isosceles triangle, I know that the angle OCB here and OBC are also congruent. So these are the same. It's congruent to angle OCB. That's because it's an isosceles triangle. So for reasoning, I would put maybe a property of an isosceles triangle. Right? And just for communication, I'm going to mark it as angle A. So here I'm going to mark measure of angle OBC. I'm going to set it equal to measure of angle OCB because we know that. I'm going to set it equal to A. So here I'll just write A, angle A, and here angle A as well. Similarly, the triangle that I'm highlighting in blue now, triangle AOB, is also an isosceles triangle. So the same reasoning, similarly. Triangle AOB is an isosceles triangle. That's because OA and OB are the same, and I'll use the same reasoning, definition of isosceles triangle. Right? So the exact same steps here, I know now that the angle OAB and angle OBA are congruent. OAB is congruent to angle OBA, and that's a property of an isosceles triangle, or you can think of it as a definition as well. So maybe I'll just copy this statement here. There. So it's a property or a definition of an isosceles triangle. And I'm going to mark that angle as angle B. So measure of angle OAB, I'm going to say, we're going to call it angle B. So here, I'm going to call this angle B, and this one angle B. Lowercase b in this case. All right, so from looking at the entire triangle, not the small one, not OAB or OBC, we are looking at triangle ABC, the big triangle that you see here, ABC. What we know about triangles is that if you add up the three angles inside, they should add up to 180. So CAB plus angle ABC plus angle BCA is 180. Okay, that's because of the interior angle sum. Of a triangle is 180 degrees. Okay, so that means if I added A plus B plus B, that should equal to 180. So 2A plus 2B is 180. You can say the same reasoning, or you're substituting, and then here I'm going to factor out the left side. 2 times A plus B equals 180. I'm factorizing here. And then divide both sides by 2, then I'll get A plus B is 90. That's dividing both by 2. Okay, but A plus B is the angle ABC, right? You see that up here, the angle ABC should be A plus B. So therefore, or am I right? Angle ABC is A plus B, because that's written that way. And therefore, angle ABC is 90 degrees. This is from diagram. And this is my conclusion by substitution. Okay. So that's the proof of angle in a semicircle theorem. It's quite long, and when we first do it, it's going to be really, really long, but you're not going to do this every time. We have like less than 10 circle theorems to study, and for all of those, we're going to prove in a similar manner.